as Wayne mentioned, we were, great friends at the LSE. So I was hired there as a philosopher of science, but as they know, I showed up and I had no knowledge of philosophy of science whatsoever. And it wasn't the first time, or nor would it be the last time somebody unqualified was hired for a job, but it happened. In Stathis and the pub above the department, so taught me philosophy of science, probably too often, too many nights. And Carl would often go to the Walthamstow pub for lunch, and I would learn a lot of philosophy of science. And so I think it's a great thing for the Western to have these two. And also, when Genoveva comes next year, then that will be the real bump in the IQ, average IQ. Today I want to talk about, so despite them teaching me all this philosophy of science, they shouldn't be held to blame, but Carl can, because I hadn't been thinking about quantum mechanics for a long time, but then Ian Weir asked me to give a talk in Barcelona on the realism of the quantum state. So, he didn't write the talk or anything like that, but if you're still guilty if you could have prevented a crime. So he's guilty in that sense. So what I want to talk about is, so ever since the beginnings of quantum mechanics, people have wondered about whether the quantum state, whether you think it was a wave function, a density matrix, however, whatever particular mathematical form you want to write it in, is that a part of the fundamental furniture of the universe, or is that part of a state of knowledge? Is it they say in physics, is it it or bit? Is it part of the it? Is there some it in the world, or is it a bit, an aspect of knowledge? And so this is this is also, you can see all the pain the founding fathers went through when you read all the correspondence about the wave-particle duality, the fact that the wave existed in this high-dimensional abstract space. So it's bad enough that there was wave-particle duality, but the fact that the wave was in a different space than what you took to be the particles is really troubling. And so what I want to do is I want to talk about that question, but I want to talk about it just from the point of view of if you're already committed to there being some extra beables, so that is some other ontology in the universe. So there are many different interpretations of quantum mechanics, as you know. And so I think that this question about how you should think of the wave function of the universe when you think that when you're already committed to some other beables, some other furniture in the universe, is most pressing here, for reasons I'll say, whereas some of the other interpretations, it's a little clearer. So I want to think about, so this is the question I want to ask in this talk is, should beable theories, so ones that are already committed to something over and above the wave function, whatever its status, regard the wave function as part of the fundamental ontology. And so you've got this wave function there, sitting there in high-dimensional Hilbert space. What should you think of it? So I think it's fairly clear that, if you're an Everettian and you think that that's all there is, well, if you don't believe in it, then there's nothing. You don't believe in anything, and so then it should be represented in some way or other. You've got to believe in it. If you're some kind of instrumentalist, then you think it's all in your head, and then there's nothing more, or at least you're agnostic about anything more. Then it seems pretty clear. What if you believe in some extra stuff? So so there's all these different classes of theories. So there's Bohmian theories, collapse theories, a whole bunch of different types of theories where you posit, in addition to solve the measurement problem, you posit some extra stuff. So, the ordinary way of thinking about Bohmian mechanics, you posit a bunch of particles in 3 dimensions, and then you have the wave function going around in a high-dimensional Hilbert space. And it's, like the puppet master, pulling the strings on the puppet of all the particles in here. And how should you think of this thing if you have this view? So most Bohmians think that you should think of this wave function as an it, and they'll whip out a quote from Bell, who says you can't even understand Bohmian mechanics without thinking of it as an it. I think I understand Bohmian mechanics, and I don't think it's an it. But on the other hand, I hate to disagree with Bill. But it's not just, I should say also, in Bohm's theory, probably better not to think about the wave function as I mean, this is just a kind of a little point, but just that it's probably better to think of the field, the complex scalar field on a configuration space that's induced by the state of the quantum state of the system as the thing that is real. And so I don't know how to draw that. I just figured it should be green. Sort of complex scalar field. But the main column is still here because you still have, now it's written in a configuration space, so it's in 3n, and then it's guiding all, it's affecting all these particles in 3 dimensions. But this is a general problem, so in other theories too. So if you believe that there's some kind of primitive ontology over and above the wave function, then the same kind of question comes up. So in the spontaneous collapse theory of Garrardi, Rimini, Weber, if you believe in, say, there are all these different proposals for what there should be in the low-dimensional space. It could be Tomolka flashes, or it could be Garrardi mass density. It could be that you interpret the theory kind of like an Everett theory, and then you don't have that, and then you're back in the Everett camp. But there's a whole class of theories, and so I'm going to restrict attention to Bohmian mechanics because that's the theory I've thought about more, and I can say more about it, but a lot of the general points will generalize to any theory that posits something extra over and above that. So first, what's the problem? Well, the problem is being lost in space. That's one way you can think of the problem. So you've got, this high-dimensional abstract space, low-dimensional physical space. So you think of this as abstract. I'm using abstract, but I shouldn't. It's up for grabs whether it's abstract or not. Is this thing real? Is that thing real? Well, it raises, it reminds you of the interaction problem in mind-body dualism, right? So you have, Descartes, positing, this, mental realm outside of space and time, and then you've got the physical realm, it's inside space and time, and then, when you teach undergrads intro philosophy or that, you then, raise the interaction problem and say, well, how do these things interact with one another? It's by some kind of magic. It's probably not the best objection because, then the reply is, well, who died and told you what causation is or how it works, but you have a similar sort of issue here, so here it's just one way, and so it's from here to there, not the other way around, so it's more like epiphenomenalism than Cartesian interactionism. But still you have, the puppet master guiding all of these particles in this other space. And if you think of them as both real, the way Bell suggests, then it is a kind of puzzle. And then, so you then have Descartes rearing his head here, and you're wondering, this just seems magical, and it's weird having this dualistic ontology with this sort of weird interaction between the two different realms. And it'd be nice if you could solve this problem. So here are 2 ways of solving the problem that have, one has attracted a lot of attention in the philosophical literature, the other one not. So one is, you could do like David Albert suggests, so you just get rid of the low-dimensional space and all those particles. Right? So Albert thinks, well, let's just take that high-dimensional configuration space, think of that as really, what quantum mechanics is telling you is that's really the arena of the world. And then there's this sort of one representative point that that represents everything. Right? So it's a marvelous point. So you could do this, and so this would be a sort of version of Bohmian mechanics on Albert's way of thinking. And then there's a lot of objections back and forth about whether it's really sustainable to be able to think like this. How would you get subsystems like me and you and desk and particles and stuff extract that all from here, and various problems with various recipes. I think in some sense that there must be a way of getting the information out because the information is conserved when you go into that representation. It's just not so easy to see how you can come out of it. But it's not really, I do share some objections. I do have some, I don't think any of the objections decisive against it, but I do think it's not it's pretty radical theory that that's all there is. It's just this massive configuration space, and we are all just this aspects of this marvelous point. Einstein, considered the thought of being realist about the quantum state evolving in a high dimensional space, and he said it was indigestible in a letter to Ehrenfest. And so many people have found it indigestible. Many people, founding fathers, tried to write the Schrodinger wave in 3 space. Of course, you know it's for non-trivial wave functions, it's impossible. But you could try to do something fancy. And so recently, Travis Norson has a kind of view where you write, so each Bohm particle carries its own wave. And then, but then it doesn't stop there, because then there are the waves connecting each of the waves, and waves, as he himself admits, it's one of the uglier theories. So, again, all the information is there. Who knows? Should ugliness be a decider about how we pick what's true? I'll leave that to Stathis to tell us. But anyway, so we're lost in space. Because neither of those options are all that palatable, and it would be nice if we could believe something else without having this kind of dualist picture. So what I want to do today is I want to suggest a kind of view that's already out there that Shelley Goldstein has, which is to think of the wave function, its status as nomological. And so then the famous old ancient question of whether it's it or bit is just whether laws of nature are it or bit. And so some views will say it's an it, some views will say it's a bit. And so it's resolved that way. I want to give a kind of motivation for this nomological view. And then I want to show how a kind of Humean trick will help against what I consider to be the major obstacles to that view. Along the way, we'll see a bunch of interesting things, I think, about why we use quantum mechanics in the first place, in some sense. So anyway, oh shoot. Yeah, so you're lost in space, and that should make you worried. Danger. Okay, yeah. We're going to come to the danger point of the paper later. So first, what I want to do is talk about this nomological view briefly, and then I want to give, the main thrust, if there's something new in the paper, the main thing is the motivation for this view, which I'm going to give. But, well, so there are these things, laws of nature. We don't know what the heck they are. But whatever they are, you might think, that what the wave function is, just is a law of nature. So the wave function of the, so psi, the wave function in the Schrodinger equation, if we use the Schrodinger model formulation, it's not, the idea here is, it's not a thing in the world. It's not, it's not part of the furniture of the world. It's not like a desk or a chair or a dog or something. It's like what H is, the Hamiltonian. So just as you don't ask, you don't look at classical mechanics and then get all freaked out and worry, oh no, where does H live? And H doesn't live in 3 space either. Right? But he never worried about where H lives because H is just part of the law. It's part of the representation of the nomological structure of the world. So that's where. So you don't ask where does it live, and is it the puppet master pulling the strings, and how come the puppet master isn't in the same space as the puppet? It's just part of the laws. So I like this kind of view. So on this picture, if you adopted a kind of Bohmian picture, then whatever the beable was, if it was Bohmian particles, Bohmian classical fields, Bohmian strings, Bohmian whatever, that's what there is in the low-dimensional space, and then that's it. And then there are laws. So then you ask the question, is the quantum state it or bit? And now the question is then, are the laws it or bit? And so this is a sort of maybe an explanation then too why the question lasts for so long, because it's really just a bigger age-old question all along. So you could take Shelley Goldstein, and he thinks laws are its. So he's a kind of, he's not a philosopher, he's a mathematician, but he strongly believes that laws are governors in the world. That there's a kind of governing conception of law. So it's an it. It's some kind of thing in the world, some kind of invisible straitjacket which is pushing things around, and it's an it. And you might worry, well, doesn't that really just sort of rename the problem? Because before we were worried about the puppet master pulling the strings of the puppet, one from the other space, and now we've got it, which is this governing conception of laws, still now the puppet master, there, affecting the particles. I don't think that's a great objection here, because that's the sort of view that the person that Shelley would have either in the classical realm or in all these other realms, and if it's a problem at all, that's a problem that people would advocate a governing law conception of laws already embrace anyway. So it's nothing special here to remove the quantum. Still, I happen to have that worry, and so you could also imagine a kind of Humean conception of laws, and thinking that laws are more like its than more like bits than more like its. And in particular, if you take something like the best system theory of laws, and where true generalization of the law can only if it's an axiom of all the best systems, that is, if it's part of the most elegant summary of the stuff that happens, the Humean mosaic. If it's the most elegant summary of that, then that's what it is to be a law. If you take that kind of view, then what you're doing is you're just taking the mosaic, all these Bohm particles or GRW flashes or whatever, systematizing, and then getting your quantum state and apparatus laws and all the rest. Okay. And so I like this view. So in this picture, you wouldn't say that psi is a fundamental beable. You'd say it's comparable to the Hamiltonian, and it's nomological. You can point out also, so it's been objected that, well, there's some disanalogies. So you think of, so this seems very contingent and time, changes in time. You can point out, first of all, that that's not necessarily true. So there, all your experience in the Bohm case is really with what the Bohmian thinks of as effective wave functions, which are extracted from the mother wave function of the whole universe. So that mother universe, that wave function might be time independent, and yet it could still have non-trivial time dependence among the effective wave functions of the subsystems. And so, we don't know what that wave function looks like. The big mother wave function of it all. We're here dealing with all these subsystems. And the main point here is that nothing in systematizing says that the function must be decomposable into functions expressible on 3 space. It's just not, it just turns out to be the most convenient way the most powerful, elegant way to describe how the beables move. And incidentally, a lot of people object to Bohm's theory in a completely misguided way because they think that their classical intuitions from Newton's third law should have to hold. And they say, well, it violates the action-reaction principle. There's a weird thing anyway. So they're saying, well, wait a second, you're saying quantum mechanics violates classical mechanics. Well, of course. But anyway, it doesn't, because there's no, you wouldn't talk about action-reaction between the Hamiltonian and the particles, nor would you in this case between the psi and the particles. Okay, here is a nice Humean trick. It's done in a recent paper by a graduate student at Harvard, Elizabeth maybe, Miller. And she notes, it's a kind of standard Humean trick, and we'll use this later, so I just want to mention it before we exit this section, that Humeans may wish to add properties to a system if it increases overall strength, informative strength, or simplicity, or the combination with respect to the beables. So suppose you had classical mechanics and you have, I gave you initial conditions, and then all these different paths were possible with respect to it. So I had this indeterminism given the initial location, position, and momentum. But then I thought, if I pretend that all those things that I can unify by thinking of scales and stuff like this, all have this feature mass, then I can get a well-posed initial value problem, where I can get all this uniqueness, and get this massive amount of strength by just grouping together all these things that behave the same way with respect to different scales and that. So I invent mass as a property, and then that gives me increased strength and simplicity. Okay. So we'll come back and use that later. Okay. So the talk is, what, like 45 minutes. I started at 20:22. Does that seem right?
Oh, you start later than that. You have until 25-ish.
Yeah.
And then another.
But what I was going to say anyway was I was going to have to shorten the talk. And this was the easiest decision I've ever made in my life. So, what part to cut is the obvious. Okay. Motivation. So we can come to that in the Q&A. Motivation. Right. So this is what I want to really do. So part of, I don't think there's the answer to the question in any way, but what's going on here a little bit, I think, is part of the difficulty when people are thinking about this what space does is the physics going on in and all this is made difficult by the fact that in the classical case and where we think we know what's going on, and the quantum case where we don't know what's going on, we're operating in different spaces. And when I long ago with Nick, we looked at quantum gravity theories, which were sort of half and half classical and quantum interact. Whether you could have a kind of half and half theory of the world, which was half classical, half quantum. And so to tackle that, you have to put everything in the same formalism. And so that's what, and I thought, well, maybe this would be useful to just jam everything into the same formalism. And you can go either way. And there are other ways of doing it than I'm going to do it here, too. But you can, so the idea behind it is, so we know what's going on in classical mechanics, what we think, and we know what's beable and what's nomological. And so why don't we just, compare, put quantum mechanics in a classical framework, and classical mechanics in a quantum framework, and then look at the differences and see whether those differences force us to reify the wave functions. So I'm going to introduce classical wave functions. Should you believe in those classical wave functions as part of the its of the world? The answer is going to be, we're going to think no, or I'm going to suggest we think no. And then ask, well, why are we going to think that the quantum case is any different? Okay, so now we're coming to, I have a shared slide with you, Bill. And so I couldn't wait all day to show you the slide. This is not it. So we'll start off with breaking news. So deep in a library in Budapest, in the National Library, scholars have recently discovered an early 17th century manuscript that's deep in a basement inside a box and another box under a table in a forgotten room behind a false wall. And so they grabbed this manuscript. And who wrote this manuscript? There's a great manuscript, a forgotten episode in intellectual history. All physicists have forgotten about it. All historians have forgotten about it. No one knows about it until you right now. Who is it? Who wrote? What is this? It's written in 1627 as the Mathematical Foundations of Natural Philosophy, which, all right, that's not ringing a bell for you guys. Think quantum mechanics. Think quantum. What title sounded like this? Okay, and who was the author? It was none other than John von Neumann. And so John von Neumann, what did he do? Well, see, he was this Hungarian physicist, and he invented, very improbably, given the history of math and physics, he invented a Hilbert-based version of classical mechanics in 1627. Published it. What did he do in this? Well, he anticipated 300 years of physics and math. It's particularly hard to do this since calculus wasn't invented yet. So that's why it was so thick. And so what he did was he introduced the Hilbert space of complex square integrable functions, psi of phi, such that rho phi, gives you, the modulo squared gives you the probability density of finding a corpuscle at a particular point of classical phase space. So, think of the vector, the classical state is rotating around in this Hilbert space, and then you make a measurement, and then you use now. I didn't think of a name for Max Born for whatever they would call this. von Born's rule or something, I don't know. And that gives you the probability density then of finding a classical corpuscle at that particular point. The theory is empirically adequate. And, in today's language, what we could say is, oh, what he did was he anticipated the Koopmanian von Neumann theorems of the 1930s that demonstrate that one can associate to every classical Hamiltonian system a unitary operator that satisfies Schrodinger's equation. So he anticipated the Hilbert space formulation of classical mechanics. So it's a little bit different because it's over phase space rather than configuration space, but otherwise it is and you can make it complex Hilbert space or real. So I think Koopman did real, the later generalizations you can do it with complex. So there are some of the references. Contemporaries objected to this view. They said, well, what happens between measurements? What's the theory about? Is the classical wave function it or bit? And von Neumann said, don't ask, don't worry, it works. And then others weren't satisfied. And there was this big, foundations of classical mechanics community having all these, conferences on the wave function and reality of the wave function and all of that. But these questions, answers to these questions were never resolved due to the plague. And so then that's how then the book fell into, became forgotten, and then that was it. Okay. So, anachronistically though, we can say, well, no, look, we did get some answers because this Englishman named Newton was born later and invented, posited a beable, the corpuscle, and a guidance equation, F equals ma, for that beable. And then you could then derive the von Neumann axiomatic Hilbert space formulation could be motivated from the statistical mechanics of those so-called corpuscles. And so the way you would do it would be you could take the classical Liouville equation for rho, the probability density for the set of particles is evolving according to this Liouvillean, and that's what it is for a single degree of freedom with canonical variables x and y. And we can introduce a wave function, psi equals rho, a square root of rho. And then it turns out that this is essentially self-adjoint and generates unitary evolution. Okay. And you can then go further and show that all the ingredients for a Hilbert space formulation exist. So you get norms, you get everything. All the same stuff you get from quantum mechanics you get in here in classical mechanics. You get this, the inner product with itself conserved, and so then that gives you, vindicates the idea that you have this probability interpretation of rho, which gives you then this probability density of finding a particle at some point of gamma space. So here you derive a formulation of classical mechanics whereby we have got a vector rotating around the Hilbert space, you've got it collapsing on states, you've got to give it, giving us probabilities by a classical version of Born's rule. You get all of that stuff. You can even then show, you can do it complex. You can look at this dissertation by Morrow, which is very nice, where you can transform into different bases. You can introduce phases. You can do, unimaginable things. It's looking so quantum you can't believe it's not quantum. And then you can then ask, suppose that von Neumann, once Newton came. Is the ontological status of the classical wave function mysterious? Well, no. You're still in friendly territory. You know how you got to this, right? You've got these beables, these classical particles, governed by this guidance equation, Hamilton's equations, and then from this you arrive at the Liouville equation and all of that, and then the rest. Okay, so that was putting classical mechanics into quantum formulation. Now we can do the other way around. I was going to, I thought, well, once the gag was done, I was going to mention, Irwin Hamilton and Werner Jacobi, but actually, the actual history actually was so close to the counterfactual one that you don't even need to do that. So here you could start off thinking in terms of the Hamilton Jacobi framework, here you've got Hamilton's famous S function, which induces a vector field on the R3n. Right, so you've got this vector field here. Then the integral curves Q along V are the possible trajectories of this n-particle system, and they solve this. So it's the guidance equation for the beables Q. And then, but then S itself evolves in time, and it does so in an extended configuration space R3n cross R, and it solves, the Hamilton Jacobi equation. Okay, so that's another version, standard version of classical mechanics that you'll get in analytical mechanics text. But now note, you can introduce a probability density rho, and then with an assumption of conservation, you can arrive at the well-known continuity equation that you'll see, everywhere. And then you can define a classical wave function, psi equals r to the EIS. Here, h is just going to be a term, with dimensions of action. And here, what you can then do is then think of psi and psi star as new canonical variables, and then show that you take a transformation from S minus rho into psi star. And when you do this, and a bunch of other things, then you can arrive at the classical Schrodinger equation that Rosen came up with in 1946. And so there's the classical Schrodinger equation. So it's like the Schrodinger equation except for this. And then you could do the reverse if you wanted. I could put psi equals r to the EIS in the classical Schrodinger equation, and then derive a continuity equation, and then the Hamilton Jacobi equation. Now compare. So here psi is a field, phi is the solution of the classical Hamilton Jacobi equation, the normals to S are the classical paths, r squared is the probability density, and this is what you get. Now, of course, if you know Bohm's theory, then you've seen you've already anticipated all the similarities. But the way Bohm originally came up with the Schrodinger Bohm's theory was he inputted psi equals r to the EIS into the Schrodinger equation, and then which then separated into real and imaginary parts, and then you get a continuity equation for the conservation of stuff. And then the quantum Hamilton Jacobi equation, or there's something else called the quantum Hamilton Jacobi equation, but a Hamilton Jacobi equation. And so here now we have Q. This Q is the well-known quantum potential of Bohm's theory, which introduces all the non-classical effects in the theory. And note that Q is this in the classical Schrodinger equation. And so here now again you have then S generates a vector field in configuration space. The integral curves along this field give the possible trajectories of the n-particle system, and then there's now a solution of the quantum Hamilton Jacobi equation instead. And all else is the same, or is it? So what you have here is this picture then of the same ontology, but now these different laws, giving you the difference between the quantum world and the classical world. And so you could have thought that, so if this is right, you could have thought that, through the quantum revolution, the ontology always stayed the same, and just the laws changed on this kind of view. Where does the classical S live? Is it a beable? And so again, S lives wherever laws live. It's not a beable. And I just wanted to note two interesting things. One is that, if you think about the classical case, sometimes when you think of quantum mechanics, you think, whoa, wait, well, how did I come into this thing? It's mysterious and signals New Age something. But no, here it's just because you had two equations, and one equation simpler. So you introduce I to take the continuity equation expressing conservation, and then the one for the evolution of S through time. And you want to condense them into two, so more power, more simplicity, and that's why I comes in there. And then also notice that the main difference between classical mechanics and Bohmian mechanics on this is just that Q switches equations. So it goes from the classical Schrodinger equation, and it's out of the quantum Schrodinger equation, and it's in the quantum Hamilton Jacobi equation, but it's not in the classical Hamilton Jacobi equation. So it's just a question of where Q is. Okay. Well, that would be nice if all of that. It would be beautiful if we could just end the talk right here, because then we'd have a devastating case for S being, interpreted the same way, both in the classical case and the quantum case. Yeah, unfortunately, obviously, there are differences because quantum mechanics is quantum mechanics. I mean, it's very different. So there's lots of different phenomena, and the theory must be different as well. But now, it's a little hard to know how to think about this section because it's not like we in philosophy have some kind of inference ticket that says if your theory has such and such, then you need to be a realist about it. So how do you know what thing you need to be a realist about? And so we can point out differences. I can point out tons and tons of differences. I won't go through all these differences. I'm going to go through the ones that are bigger. But you can point out, so of course, there's the Q in the one Hamilton Jacobi equation, but not the Q in the other. Does that mean you need to be a realist about the S? Well, why? That doesn't, I don't see why. The evolution equation is linear, of course, in quantum mechanics. It's non-linear in the classical mechanics. So does that mean you have to be a realist about it? Well, why? More detailed type ones. Size single valued in QM, not single valued in classical mechanics. It's going to be related to some things that come up. The sense in which psi is prior to RNS in quantum mechanics, and RNS is prior to psi, sort of think about nodes. But again, that doesn't seem like a big difference either. There are differences though. So in the von Neumann case, the big difference is that if I input something like R to the IS into the Schrodinger equation in the quantum case, then I get these two equations we've already seen before. If I do it in the, now I'm not doing it in that Rosen equation, but the one from the von Neumann, then I get actually the same equation for both the phase and the modulus. And so it's kind of an interesting insight, I think, regardless of whether this makes a difference or not. But Mauro in his dissertation says, what is quantum mechanics? Well, this kind of view, what the main innovation of quantum mechanics is that quantum mechanics is the theory of the interaction of a phase with a modulus. So it doesn't happen in the quantum. It doesn't happen there, but it happens here. But I don't want to work in that formulation. Let's think about the Hamilton Jacobi. So in the Hamilton Jacobi, you can see a big difference. Here's a way to motivate this too. So if you read Holland's book, where it's all Hamilton Jacobi equation, throughout, where he motivates quantum mechanics with Hamilton Jacobi theory, you might look at that and think, how can anyone read Holland's book and yet think that the wave function is real? But of course, Holland presumably read Holland's book, and he thought that the wave function was real. Well, what's going on? Why would he think that? It's not for any of those little sort of more techie reasons that I listed. It's for what determines the motion. So what do you need to determine the motion? In the classical case, you need your initial position, velocity, and potential. And the S function just generates a global ensemble. And so the exact evolution is independent of a classical wave function. So you don't need the S function. In the quantum case, you do, to get the exact motion. Okay. Since I'm running short on time, I'll just resort to pictures. So classically, so suppose you've got some trajectory. So there's one. This is a nice example from Holland. Well, you could have, S describe an ensemble of parallel straight lines of momentum p generated by varying the initial position. And so I generate the ensemble by varying the initial position. But I could also have done it this way, where I varied the initial momentum. And so I don't, so I just don't need so it generates this ensemble, but to get the exact motion, I don't need it. And so that then, so as Holland puts it, he says, in classical mechanics is not a causal agent. S is not a causal agent in classical mechanics. Whereas in Bohmian mechanics, it is. Now, bring in the Humean trick. Okay. So just because something was needed for getting more accurate, stronger strength, better predictions, doesn't mean that you have to be a realist about it. You might introduce it to get better strength and predictions. And so just as you might have introduced mass here, you can imagine introducing the S to get generate the unique motion. So you don't need to be a realist about you don't need to, you can think of so if you were inclined to, maybe now we're getting now to a point where only I occupy this sort of territory in logical space, but if you were inclined to do to the M in the classical case, what a Humean might do, then it is natural to then think of doing the same thing with the S. Okay. And so that seems to be the biggest challenge, and this seems to be one way of surmounting it. And then once it's surmounted, then you have then really the analogy is holding up otherwise. Okay, 2 small points and then I'm done. So there's this thing, so now we're done with that whole. We're done with the official portion of the talk, and now we're just noting a couple of incidental things. So one is, there's this objection, God, it annoys me, from Everett all the way through till yesterday, of Everettians saying that Bohm's theory is just Everett in denial. Okay? So this is their objections. They say, so I call it the redundancy argument. And so here it is in Everett. It says, our main criticism of this view is on the grounds of simplicity. If one desires to hold the view that psi is a real field, then the associated particle is superfluous, since as we have endeavored to illustrate, the pure wave theory is itself satisfactory. And so Brown and Wallace, Deutsch, Wallace again, Zay, a bunch of people have made this claim. And then there are responses. Some of the responses actually I disagree with even more than the objection. Typical sort of, the friend of your, really communist type, small differences you hate more than the big differences. So the idea is, so from the Everett point of view, they're thinking, well, I've got all these cats, and you Bohmian, you've got one too many. I mean, first of all, you think of the nerve of the Everettian to be making any sort of objection about ontological parsimony. It defines the least. Okay, it's true if they're right that if there really is, so suppose the wave function is, there are all these different components of the wave function generating all these different cats. I suppose you really do have a cat composed of wave function stuff, and then they're thinking, well, then you also have all this particle cat. What's a particle cat to do? You've got a particle cat so you've got 2 cats where there should be only one. And so it's redundant. First, I'd like to just point out, that of course assumes that they do solve the measurement problem, and the measurement problem and the probability problem, which is an ongoing problem for Everett, is they're a package deal. I don't think you solve the one for the other, because I think what a cat is, so if you think of it in a kind of Ramsey-Simpson sort of way, what is a cat? A cat is some kind of furry thing with 4 legs and meows. It is probabilistically distributed according to Bohm's rule. Anyway, and then they have various objections to force the Bohmian to treat the wave function as a beable. I think those fail, obviously. But anyway, the point I wanted to make is that if you take this perspective, the one I'm adopting here, then Bohm is really more like the opposite of Everett. Right? Because you've just got the particles and no wave function stuff in terms of the its of the universe. In Everett, you've got the its, the wave functions, the it and no particles. And so they're really like the opposite. And so then they really have some nerve to make this objection. And the second lesson, so there's been a lot of talk in the foundations community about this theorem, the PPR theorem, about what is supposed to rule out certain interpretations of quantum mechanics. And the way they phrase it is whether, the question is whether the wave function is ontic or epistemic. And the way they understand ontic or epistemic, I don't have time to talk about really, but the idea is whether if you had full information about everything that you believed were the parts of the its of the universe, could rational agents then posit two different wave functions? If you're ontic, if no, epistemic, if yes. And then people point out that there's two types of, and so they're called psi-epistemicists and then Scientologists. It's supposed to be. So, and then people point out, well, there's different versions of psi-epistemicism. There's one where the wave functions are epistemic, so it's in your head, and there's some underlying ontic state. And then, oh, whoops, this is supposed to be one. Yeah, this is supposed to be one, sorry. So, yeah, well, the next slide is, yeah. Oh, yeah, I fixed it on one slide, not the other. So the PBR theorem is supposed to rule out this, but then leave this kind of thoroughgoing instrumentalism on the table. And it would be surprising if some sort of theorem disproved instrumentalism in general. And then so then you're supposed to be either a kind of instrumentalist or this kind of Scientologist realist. What I'm trying to show is that not all Scientologists believe that psi is part of the ontology. Right? It's not. So there's just as there's two meanings of psi-epistemic, there's really two meanings of psi-ontologist. And so ontic, in their sense, doesn't mean necessarily ontological. So just like you could be, Mach could believe in, not believe in forces or something, even though forces would be necessary to generate the motion, so too you could have that kind of view with the wave function. And that would mean that you're a Scientologist. It would mean you're a Scientologist, but not believing that psi was part of the deeper ontology. So the conclusion is, that we're not lost in space. We tried to motivate a nomological understanding of psi. Showed how this Humean understanding helps surmount an obstacle with this view. And the upshot is that it is possible then to think of the quantum revolutions changing the laws but not the ontology of the classical world. It's also kind of insightful for thinking about it all in terms of the history of wave-particle duality. So here you're either putting in the waves or squashing out the waves. And there's a one wave squashing out the waves. And instantly it removes two objections to Bohmian mechanics. There's redundancy objection and the action-reaction objection. And just as a minor refinement on our understanding of PBR. Thank you.
So we have another 10 minutes for questions. Wendy?
Thank you, Craig. I like this a lot. There's lots of things that I like about this talk. One is that I think it's an object lesson in not being too hasty in taking a particular formulation of theory and trying to read the ontology off of it. I think one lesson is if you want to know what the ontology of a theory is, you have to think very carefully about what the role various things play in the theory. So I guess a couple more comments. One is minor comment about the PBR theorem. Actually, can you go back one? Where you go back where it rules out number one. It almost but not quite rules out number one because there's an extra premise in there that whatever the underlying ontic state is, it's possible to do independent preparations. So if I do two different preparations at different places, then the probabilities are independent. And because that's Rob Specken's response. He's a psi epistemicist, but he has this thoroughgoing holism where anything you do anywhere is intrinsically involved in everything else. So he, even before the PBR theorem, he had rejected that independence condition. But it seems like a poorly, I'm sorry. Okay, when Rob talks about it, it seems poorly motivated, but actually on something like a Humean view, and I'm not sure if a Humean view is an epistemic or ontic view of the wave function. If the wave function is merely meant to be some kind of pattern in the underlying mosaic, then the wave function I attribute to a given particle actually is not a local fact about the particle, and would actually maybe motivate violation of that independence.
I haven't, yeah, so there's obviously there's a lot of back and forth about whether the PPR theorem is sort of deep or shallow, and does it rule out anybody at all. I guess maybe to ask your question about whether, so I've never studied Speckin's interpretation.
Well, let's say there is no, he doesn't have an interpretation, he's got a promissory note that he's going to someday develop an interpretation.
Yeah, so are there beables? I mean, so if we were going to ask the question about the Humeanism, so the Humean is going to need to systematize something.
Right.
So what will the Humean systematize? So if there's something there to systematize, it could be that.
Yeah. Yeah.
Otherwise, then it does start looking more like,
Yeah.
it does not. So the Humean can't, there's nothing to systematize there.
Yeah, thanks, Greg. This was great. I have a question about the Miller move or so, which I guess you want to use analogously for the S in the Bohm's theory. What I don't understand is why. So there would be what really the status of the masses are, because I mean, given so we have underdetermination or no determinism without these things, and then once we postulate masses, we have this massive increase in predictive or explanatory power. So somebody might think that's a reason for positing that these guys are, that this is a property that's part of ontology. Like somehow, I mean, in this argument, that's supposed to be denied, right?
Say that last part again.
So the idea, so if we add properties to the system, that increases the informative strength. But so how are we supposed to think of these properties? I think the way one is supposed to think of them is as they're just some kind of crutch. But I mean, there's some kind of seemingly natural way to go. It's like, well, look, we have these particles have an additional property, and that's part of the inventory of the world, because some kind of inference to the best explanation. I mean, this, if we posit this, we just have this tremendous increase in predictive and explanatory power, so it must be something real.
I mean, I guess I think, I think of it, so I think of F equals MA, and people will say, well, what are the theoretical terms there? And they say F, and then they say, what are the other one, the non-theoretical terms? They say M, and then A is a position in time. But then I've always thought that was I think I'm not alone, thought that was a mistake, that M was just as much a theoretical term as F. So I think that M there has the same status as the F. And so whatever status the law then has, that's what status M then has.
But just saying that it's a theoretical term doesn't mean we're not, I mean, then you're already being committed to some kind of instrumentalism that way, so that can pick up.
Oh, about the M,
Yeah, I mean,
yeah, it's not part
it
of
might
the
be a
mosaic.
theoretical term, but you might then still be moved to think that must pick up, latch onto something in the inventory of the world.
Well, it's not part of the inventory of the, in this kind of way of thinking. So I've got a bunch of, I've got a manifold with a bunch of things with position at different times, and then from that I extract this mass, or attribute this mass to help me get unique evolution. But it's not part of the inventory.
Yeah, that's what I'm not seeing. I mean, so I start with the basic inventory, position of momenta, or no, I guess P's are, then I already have the mass in there, so I have momenta, positions of velocities, I suppose, because P's are already pretty.
Think of it as all just
Those can't be P's, right?
It's just all positions. Just positions. I get a 4 manifold with a bunch of positions.
Okay.
In both
So what are these
classical
P's
and
are? What are these P's doing? That's just.
Oh. Yeah.
So just I already found this later. I thought, okay, start with your positions, and then there might be various reasons that move you to attribute additional properties to the stuff that you think is real properties of these things. And part of the reasons might be that it massively increases your predictive explanatory power. So that's and if a move like this goes, then of course the question is whether you will do the same thing before.
Oh, you were asking, are you asking like the prior question, how does the Humean know what's a systematized versus, what's already given and what's to be systematized? I don't know. Yeah, so that's a big question for the Humean. Yeah, because of course all the reasons that you give for thinking of the mass here are maybe reasons for thinking that the mass is actually on the in the mosaic.
Right.
Yeah.
Exactly. Yeah.
But then but you could do the same thing. But then I could go to other types of properties as well.
Yeah.
And now all of a sudden you've gone from a beautiful spare plain landscape to this disgusting property-filled thing where no limits. So what?
The real world.
I could add desks in and stuff, clowns.
I think there seems to be a few follow-ups. I think you were the first there.
Yeah, but this is what I did in the relational regularity account of relational mechanics. But there I took F and M as being part of the mosaic, and then you get a nice law that says, look, if there are frames in which F equals MA is whole, where A is understood as the frame dependent, and then you notice that A is actually the same in all of these frames. And so the absolute acceleration looks like a nice kind of supervenient quantity that you didn't have fundamentally. And so that might answer, take as a very big premise that you're kind of motivated by relationism. Right, and then, whatever motivates you for relationism, if you buy that kind of picture, that does motivate you now to think of the absolute accelerations not as fundamental, but as sort of supervenient on the Humean mosaic. So you were asking, could there be any sort of motivation?
Yeah, so what Nick said.
You have masses in the picture.
Well, yeah, but it's an example. It's the same idea. Yeah, so,
I mean, in a way, it makes the problem worse, right?
Yeah.
Each one of us is right.
Well, there are quite a few people who want to ask questions, but I think you were next in line.
Okay. I have a couple of questions. I like a lot, this view. One is, if I understood well, you can understand, on Goldstein or similar way of thinking, the wave function is two different things. One is a parameter in a law, and the other one
is a what?
A parameter in a law. There is some paper in which Goldstein talks about it. So you have a dynamical equation, and then the wave function is like a parameter in this law that actually. Another way is to understand the wave function is basically giving you the relationship between the dynamical properties or the properties of the systems. So they're not themselves, guiding, but they're encoding information about the correlation between the evolution. So if you could say something about that. The other question that I have, is about the picture of the quantum states as a field in a higher dimensional seems strange, because how can it influence the particles? But isn't it also strange, to talk about field, normal field in, three-dimensional space influencing the particle? Do we understand the type of question?
Yeah, that's probably why it's not the most solid. It's probably just an intuition pump rather than something stronger than that.
Okay.
Well, I'm not sure what you meant by the second way. So when I was saying quantum state, that was really sort of shorthand for not just the quantum state, but the whole, Schrodinger equation or whatever, linear quantum equation that you were talking about. So I meant not just the quantum state in isolation, but the, it as part of the law. Is the other view you mentioned one of these kind of, having dispositions of the of the particles? I've seen that view out there, where you think of the Bohm particles as having this disposition. The what the wave function is really doing is representing all these dispositions of all the particles.
Yeah, you don't have to think about it as disposition necessarily, but it's kind of code information about, I mean, and it's in a higher dimension just because, I mean, the information is very complicated, but it's not really adding anything. I mean, to the
Yeah, I mean, that's more or less my view.
Yeah.
So time maybe for one last question. Who are next?
No, don't.
No? Okay.
Just about what you said at the end about the average versus Bohm, I know it wasn't the main part of your talk, but since you brought it up, I just thought it was worth commenting on. I wasn't convinced by your response to the Brown-Wallace objection, because you said, you know, what nerve do they have to talk about parsimony, and variance and all that. But obviously the crucial point is that they're not modifying the Schrödinger theorem and they're keeping everything unitary. And so I think from their perspective, what they would say is the parsimony is in the fact that if you can get away with what they would call branches, the various branches, then the lack of parsimony is in the fact that you're adding to the you're introducing new dynamics to pick out one of the branches. So
Yeah, I agree. I mean, you know, so I'm not making the point about it. I mean, they don't really make a big deal of the parsimony point either in this debate. It's really just that it's redundant. You know, this extra particle ket hanging around is you've solved the measurement problem twice now if you've solved it once. So that's really the more of this. I mean, you can get into issues about whether that theory is parsimonious or not. Obviously, in one sense, yes, and in one sense, no. But yeah, that's not the main.
right, no,
Yeah,
I get that's not the
that's just a rhetorical excess.
Okay, so time is up. If you have your question, maybe you can ask them.